So I think we have essentially completed the construction of the states, or actually their coordinates in the position eigenvector basis. So whichever one you need, you just work out this algebraic operation. Algebraic operations are easier than finding solutions to partial or second degree partial differential equations. So it is algebraic. That's the superiority of this method really over the conventional Schrödinger equation method. So let's try to elaborate further on other properties of this interesting and simple problem, harmonic oscillator. For instance, we may be interested in asking the question, what is the uncertainty in the ground state involving x and p? Right? That would be a nice question to ask. For instance, what is this delta x and delta p in the ground state? I'm not planning to carry out all the details because that some of it are trivial arithmetic or mathematics. So what you have to do then is delta x squared. Well, I hate this book's notation. I guess this is really cumbersome. The old notation will be just delta x and delta x squared. But you know, he is trying to be very rigorous, so it is this expression, right? What is it? X squared minus x squared, as we have worked out. And if you are doing it in the ground state, that's a shorthand, you know, GS meaning ground state. So what we have to do is compute all these things in the ground state. Let's do it. For instance, what is x? X is dx x psi 0 x squared, right? Minus infinity to plus infinity. You immediately see that it's 0 because that's the Gaussian, right? The number, this is the n0 squared times e to the minus x0 squared divided by x squared. Psi 0 have a factor of 1/2 in here. When you take the square, that 2 goes away. And that's even under x, and that's odd. So you change the sign under the integral sign, so you get equal to itself. So this automatically vanishes. You don't need to carry out the integration. It is by symmetry arguments, it's easy to see that it vanishes. And when you compute the x squared, again the same thing, the x squared divided by n squared times x squared x0 squared. And you can compute this easy. This is no problem. You can work it out. And let me tell you how do you work it out, really. A trick, and I will write the result down instead of doing it. Remember, I told you that there is this, the generic Gaussian integral. What is the generic Gaussian integral? dx e to the minus alpha x squared, which I have briefly summarized in half a minute how to get this result. That's a generic Gaussian. If you need, so let's call it the 0. If you need the so-called I2 dx, you can only talk about the evens, x squared or x to the 4, x to the 6. The odds vanish due to the symmetry argument I mentioned. You change the x to minus x under the integral sign and you get it's equal to minus itself. Only the even numbers survive. So if it is this one that I'm interested in computing, how do we do that? You may think of sophisticated things, etc., 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 but there's the so-called parametric integral or parametric derivative. What does it mean? This I can write as d by d alpha e to the minus alpha x squared, right? Obviously, when you take the derivative with respect to the alpha, it brings down minus x squared. This minus is to take care of it. So this trick is really very nice. So you take the minus d by d alpha out, and you have it's reduced to I0, which is this one, square root of pi times alpha to the minus a half. When you take the alpha to the minus a half derivative with respect to alpha, it is minus a half and minus is plus a half. So plus a half, so it's 1/2, so square root of pi there, and alpha to the minus 3/2. So the result is this. So I can really copy that result in here to write here. what is here? My alpha is 1 over x0 squared. The alpha in this example is 1 over x0 squared. Therefore, I can write the x squared expectation value as n squared. This was the ground state normalization constant times square root of pi over 2 and alpha to the minus 3/2. So it is, alpha is 1 over x0 squared, so x0 squared to the plus 3/2, right? There's a minus and this is in down, so it is plus 3/2. So the result is then n squared pi over 2 x0 cube. That's n squared times x0 cube. Let me finish this computation. I'm not going to repeat it for p and delta p. It is an educative little exercise in this context. That's the reason why I'm spending a little time on it. Now, let me substitute the n and the x0 as given in here to finish this computation. X squared is then square root of pi divided by 2. N is this. The square of it is 1 over pi to the 1/2. That is 1 over pi. And 1 over x0. Okay. That is n squared. And x0 cube, the pi's cancel and we have x0 cube cancel, so x0 squared divided by 2. You see how simple it became, and if you substitute this expression in, this is x0 squared. Remember the definition here, it wasn't x, it was x0 squared. So it is h power over 2m omega. Did I make a mistake? It looks as if. Where did we do the mistake? Let's check. X squared. N is, there's no problem with the n. And alpha was 1 over x0 squared. It should come out to be independent. No, it looks okay. I'm sorry. Sometimes even the dimension is correct. At first, I was disturbed whether the dimension was incorrect, but this has the dimension of length anyway, before putting in the explicitly. I was computing something of dimension of length squared, and this is the dimension of length squared, so it's consistent, no problem. So this is the x squared expectation value. As x expectation value we have demonstrated to be 0, so this is really what I call delta x squared. This one, right? This delta x squared. Now we have to go through the delta p squared. Now what is delta p squared? Delta p squared expectation value is p squared expectation value minus p expectation value squared. Now let's check whether there are any symmetry arguments working for this case as well. So let's go through the p expectation value, for instance. In the ground state, dx psi 0 star p psi 0, well, it's real. I'm just trying to be rigorous by putting the star in there in this language. So what is the p then? It is h power over I. In the space of functions of x, it is h power over I d by dx. We have demonstrated this before. On the position eigenvector basis, it acts with a sign, and on the coordinates, it acts with the opposite sign, so that everything compensates with each other. So it's d by dx. So d by dx acting on the psi 0, which is e to the minus a constant times x squared. It brings down a linear x. That linear x, again, it converts this really to previous thing. What is it really? This is minus I h bar. There is another minus a half to x0 squared times twice x. That is what this derivative brings all the way down 2's cancel, minuses cancel. So you have I h bar x0 squared, which is a constant, times an x, which is sandwiched between this and that. Psi 0 squared is Gaussian and even in x, and there is a linear thing multiplying it. Therefore, changing the variable x to minus x under the integral sign, you get the p expectation value 0. You may say, well, you didn't have to go through all this trouble. It was more or less obvious. If you could feel it, fine. But this is safe to demonstrate. Okay, so p expectation value turned out to be nicely 0. So what is the next step? It's the p squared that I have to carry out. So let's do that. P squared is dx psi 0. P squared is minus h bar squared d squared dx squared psi. So h bar over I squared is minus h bar squared, and d squared dx squared. It is not a trivial matter. You have to be a little careful in here. d by dx again of psi 0 was minus I h bar minus 1 over 2x 0 squared times 2x on the exponential. Let me simplify. So it is I h bar 2's cancel plus I h bar x0 squared, a constant x times the exponential. That's the derivative. If I now have the second derivative, right, d squared dx squared on psi 0, I will have a factor of this. Fine, let me move it out. And these constants are important. And then I have to act this derivative on here. So e exponential, because the derivative of this is 1, minus this entire thing again. I h bar x0 squared, and then it comes down an x squared times an exponential. Correct? Let me check. No, there is no IH bar. The derivative acting on 1/2 of that 1/2 goes away, so it is x over x0 squared. That's the derivative. And there was a first term x squared, so this is correct. This is consistent. So here, 1 minus x squared divided by x0 squared exponential. Taking the derivatives, as I said, I'm sorry for this pedantic exercise on the board, but to get this as the dimensionless number, as the first term is 1, is a check of the correctness of the consistency check of the correction, right? If I was having another dimensionful quantity, I would be making a mistake. Then, the first term, perhaps you have to make a note of it. The first term is x there, and when I'm taking the derivative of e to the minus 1 over 2x0 squared x squared, 2's cancel, and there is an x divided by x0 squared. That is x times x is x squared divided. So it's consistent. Otherwise, I would be making a mistake anyway. So this is the second derivative. Then you substitute it in and compute that integral. Please do it on your own. As I said, it's not a very good idea for any professor, including myself, to try to do such stupid things on the board, but I still attempt to do it. So what you get is 1/2 h bar m omega. So the result is 1/2 h bar omega m. Fine. So where are we now? We have demonstrated that the expectation value of p is, because of the symmetry, it's 0. So this is delta p squared expectation value really. 1/2 h bar omega m. Now we are there. I can write the now uncertainty product delta x squared times delta p squared, which is equal to delta x squared was h bar over 2m omega, and delta p squared is h bar omega m divided by 2. Omega m's cancel, and you have h bar squared over 4. So that's really the point I was trying to make. Delta x times delta p, say, let me use this shorthand, symbolic. Instead of delta x squared, expectation value square root, that's too cumbersome a notation. Delta x is the uncertainty, taking the square root of this thing, is h bar over 2. A beautiful result, really. So this ground state is a minimum uncertainty state, because in this delta x and delta p really satisfies the minimum of that general uncertainty that we have demonstrated, which would be always larger, or in the very special case equal to h bar over 2. This particular state turned out to be having a minimum uncertainty state. But I invite you to work on your own that the excited states are not minimum uncertainty states. The product delta x and delta p will be larger than h bar over 2. As a matter of fact, the result is n plus a half squared times h bar. So this is the ground state. And for the general states, the delta x squared, delta p squared is equal to n plus a half squared times h bar squared. Let me write it in slightly different way, not the way Mr. Sakurai is doing, but let me do it in the following way. Let me put the 2 in here and take the 4 out, showing you that it is h bar squared over 4 times a number which only is equal to 1 in the ground state when n equals 0. For all the higher states, there is something big. Otherwise, that's the overall factor multiplying the h bar squared over 4. Try to construct it on your own. It may not be a trivial exercise, I warn you, because it requires that you have to be able to work out those algebraic expressions that I have derived for getting the higher states. And it may require some really algebraic, beautiful, but difficult manipulations to work this out, but that's the result. 2n plus 1, I hope it is readable from that distance. That is 2n plus 1. Overall squared times h bar squared over 4. So that really essentially finishes the discussion of the actual construction of energy eigenstates and energy eigenvalues of the simple harmonic oscillator. Now let's elaborate in the remaining time on some of those further properties of the harmonic oscillator. Let me remind you first the result that I have obtained for the time dependence of the x and p operators by utilizing the Heisenberg picture. I have demonstrated that xt was x cosine omega t plus p m omega sine omega t. Schrödinger picture operators, right? That is the value of the x at x equals 0, at t equals 0, when the Heisenberg and Schrödinger pictures coincide. These are the operators in the Schrödinger picture, that is the values of x and p at t equals 0. Let me not write it explicitly because we have really worked it out before. So what is the pt? Pt is p cosine omega t minus m omega x sine omega t. Notice that the dimensions also match. And these two operators in the Heisenberg picture oscillate like the classical ones, right? They oscillate with omega. What is omega? It is the classical frequency. That's what we have carried over from the classical physics. So they oscillate with classical frequency. That's nice. Question. do xt and pt also oscillate with classical frequency? With the same frequency, I'm not writing it. Is that valid for those expectation values? It is clear from the explicit expressions that the operators directly oscillate. Let's check. This is it sounds like a difficult question, but it's not, but an important question. Let's check it. If the state here, whatever the state, psi and psi, is n, for instance, an energy eigenstate, what do you get? What we get is n x of t, and n is n x n cosine omega t plus n p n sine omega t divided by m omega. Okay, I draw your attention to this expression. What is this? 0. Remember, x do not commute with h or n, p do not commute with h or n, so they are not diagonal in the n basis. So this is really 0. And that's 0. That's 0. Wow, it sounds like a paradox, right? Not really. Again, that we should be glad. At first, we may be shocked a little bit that we get this strange looking result. We say, yeah, of course, that's what we should have gotten, because we know that stationary states are those time-dependent states in which expectation values are time-independent. An energy eigenstate is a stationary state. Explanation of this seemingly strange and shocking result? Yes, indeed, it's very natural. We should be grateful that it is so. If we get something non-zero, we should have been disturbed, really. Explanation: energy eigenstates n are stationary states. Therefore, the expectation values in this state should be 0, as is the case for any stationary state, as I have demonstrated before. So that's nice. How do we get oscillations at the expectation value level? In order to really have consistency or correspondence consistency with the classical physics, there's a way out. That's a very profound issue, really. The way out, how to get oscillation, To observe oscillations, we need to consider superposition of energy eigenstates. Perhaps you remember the spin precession problem, which you had the pleasure of spending a lot of time in the exam, as compared to single state versus superposition of states as the initial states, and how do they evolve in time, that's really again the same. In the pure energy eigenstates, single definite eigenstates, they don't show any oscillation, but if you consider superposition of eigenstates, for instance, if you choose your psi as C0, 0 and C1, 1 as the simplest, you can think of the most general version if you want, involving all the infinite states, energy eigenstate, but let's take the simplest, this one. What do I get for the psi, xt, and psi? Well, it will be quite involved, really. It will be C0, 0, C1, 1. That's from the left. And you will substitute this expression in, that is x cosine omega t plus p sine omega t over m omega in this side, and then C0, 0, and C1, 1. And you have to compute all these expressions. What do I have? Obviously, the cross terms only will contribute. The direct terms, take this as a lump for the time being, because both x and p are non-diagonal. Therefore, as far as this non-diagonality is concerned, there's no problem. So if it is between 0 and 0, it will give you 0. It's 1 and 1, it will give you 0. So it's going to be either 0, 1, and 1, 0. That is, it's going to be 0, C1, 0, the entire lump, and 1, plus this one, C1, 0, and C0, 1, an entire lump, and 0. Now, it's, from this point on, it's easy, because what you need here is, you need to write the matrix x and 1, and 1 and 0. Right? For the x terms, you need 0, 1, and 1, 0 terms. Similarly, for the p terms also, you want 0, p1, and p0 terms. But we have worked out, and we know the matrix representations of x and p for between m prime and n. You write them in, and then you should be able to come up with a nice oscillatory form. Perhaps I can give you the explicit form for you to check and enjoy yourself. If I can find it among my notes. Yes, I do. For example, I assign this as a private homework. Please finish this. Show that it is h bar over 2m omega twice C0, C1, C0, C1 star cosine omega t plus a phase delta. For instance, if it is, this was sort of something quite simple that you can come up with. If you feel more comfortable, you can manipulate these a little further, but an amplitude time a cosine of omega t plus a phase is really something which shows that it oscillates. And it's consistent with the correspondence, via the correspondence principle with the classical results, and that's quite satisfying. Let me, before finishing today, comment on something more involved. Although we are not going to move into that subject in this class, as you have been equipped with the formalism eventually you may even wish to use it in your own research, I don't know, whichever field you are going to proceed. If you are moving along the way quantum field theory or quantum optics, you will need that particular tool. So let me ask the following question. We have seen that the ground state was a minimum uncertainty state. That is, when you compute the minimum on the uncertainty product in the ground state of a simple harmonic oscillator, you get h bar over 2. It's really the minimum value that that product can take. But the excited states are not. So there is an important question. Can we find states in terms of a superposition, of course. The definite states obviously do not have that property. Can we find a specific superposition of energy on eigenstates in which the uncertainty product is minimum, so that which would really mimic the classical oscillator most? It is the closest to the classical oscillator, right? Is there such a state, general state with minimum uncertainty product? Well, those states are called the coherent states. Very important subject, really, especially nowadays in the context of quantum information theory. They are entering into the picture in a strange manner. So the last issue that I would like to comment upon, I'm not going to go through it, are the coherent states. Coherent states are defined as the eigenstate of the annihilation operator, strangely. Well, annihilation operator A on the energy eigenstates N has the lowering, right, ladder role. It decreases the number by 1 unit. But of course, you can define its eigenvalue problem. And if lambda is its eigenstate, and so I denote the eigenvalue with the lambda as well. Then you can show that these coherent states have minimum uncertainty products. Also have the minimum uncertainty product. Second, when you expand them in terms of the energy eigenstates now, and you can, for instance, question, is this a complete and orthonormal set? Ask yourself. Question, completeness, orthonormality, I'm not questioning, because you can always, that's also a very good question. Why? A is not Hermitian. We have a general theorem of having eigenstates of a Hermitian operator corresponding to different eigenvalues are orthogonal. You can normalize, make it orthonormal. This is not Hermitian. Even orthogonality or orthonormality is at stakes. You see, it's a very strange completeness. Question 1. Question 2, orthonormality or orthonormality. There is no guarantee, probably they are not satisfied. If they are not satisfied, you cannot use it as a basis. However, you can expand it in terms of the good bases, which are the energy eigenstates. You can expand it, obviously, as n starting from 0, we know that it's true, fn and n, that can be done, because n is a good basis. Question, try to invert this, try to express n in terms of lambda. You ask me them back, what about these? Of course, without understanding those, you cannot really invert it, because you don't know whether lambda is a basis or not. You don't know about the completeness, you don't know about the orthonormality. Very challenging, beautiful questions. I invite you to work on them on your free time. I promise that you will not be responsible in the exam, because these are difficult questions. But anyway, fun questions. For example, the distribution fn squared with respect to n is the Poisson type about some mean value. But this fn has that following beautiful distribution. Fn mod squared is n bar, which is the average, divided by n factorial. How nice. Some of you may say, I know what that distribution is. Those of you who are experienced in statistical mechanics. What is that distribution? What type? Poisson. That's a Poisson type of distribution. That makes it also a very useful and very relevant thing in quantum optics. That's also an interesting property. Yes. And another thing, you let it evolve and look at the time evolution of these states and check the uncertainty at all times, and it is retained. The minimum uncertainty is not spoiled, and it stays minimum uncertainty state at all times. Minimum uncertainty states and survives in time. Survives, this is a further property, survives in time. You see how an interesting field this is. There's so much to think about and to enjoy yourself with. So I think that's a good point to stop the discussion of the harmonic oscillator as a package. We have really discussed everything about harmonic oscillator from all respects. So it takes us to the threshold of a new subject, which we will start next week, which will be path integral formulation of quantum mechanics. I will directly jump into path integral formulation. It is such an interesting subject. It's an alternative formulation of quantum mechanics, developed single-handedly by Feynman during his PhD thesis in 1950s. And for certain problems, it is more insightful to understand the global properties of the systems. So I will skip some of those subjects as I have mentioned along the way, and I will jump into path integral. I hope next week, in the first bracket of next week, the morning session, we can finish it, and we can move into the gauge problem in the afternoon. So the next week will be an important block in our semester. If we cannot finish, we will continue, of course, because the gauge problem of quantum mechanics is an interesting one. Eventually, it will evolve into Aharonov-Bohm effect. If I find time, I will talk about magnetic monopoles. And also Landau levels, briefly perhaps. Landau level problem is discussed in your undergraduate 431 in detail. At least I do that in 431. So we'll see. As time permits, we'll try to cover as much as possible. Otherwise, don't. Okay, that's all. Thank you.